Welcome dear students. In this video, we will learn some more concepts related to. So first of all, we will calculate the work of a force during a finite displacement. So as you already know that if a force is acting on any particle or a rigid body and there is some small displacement dr, then the work is equal to F dot dr. This we already know, and we can write is F ds cos alpha. Okay. Now suppose this is your element. Okay. So suppose it is the initial position is this, and ds is the small distance through which this element moves because of the action of this force. Now work for a finite displacement from point A1. So this is the initial point A1 and this is the final point A2. Okay. So this work you can calculate by simply integrating this expression f ds cos alpha. So f cos alpha ds from S1 to S2. Okay. So by simply integrating, you can calculate the total work of which this force do on this particle when this particle moves from point A1 to point A2. And similarly, you can calculate the work for the couple. So if some couple is acting on any particle and because of that couple there is some rotation d theta, then the work is du is equal to m d theta, and for a finite rotation the work will be m integral of theta 1 to theta 2 d theta, and finally you will get m theta 2 minus theta. Now let us see the work of a force during finite displacement for some situations. So consider this first situation when your particle is either moving up or moving down. So this is called as work because of a weight. Okay. So we know the work is equal to because the small displacement is dy, then small work du is equal to minus w dy. And suppose this weight moves from point A1 to point A2, then the work during this finite displacement u12 will be integral of this w dy from minus y1 to y2, and this work is negative because uh, both are in opposite direction, displacement and force. Now when you integrate it, you can get this equation wy1 minus wy2, and which is equal to minus w delta y. Okay. Similarly, suppose this is the spring, so work of a spring. So in the undefined form, this is the undefined form of the spring, and suppose it is deformed slightly to x1, and then spring force will also act in the opposite direction to this deformation, and suppose this is the final position. Okay, so we know that du is equal to minus f into dx because they are in the opposite direction. Now spring force, we know we can write spring force by this expression f is equal to kx. So in this expression of work we can write kx dx, and for this finite displacement we have x1 to x2, and when you integrate this then you will got half kx1 square minus half kx2 square. Okay, so this is the work from a spring, and this work can also be calculated with the help of this diagram. Okay, So suppose on the x-axis we have taken the displacement, on the y-axis we have taken the applied spring force, sorry. So then work can be calculated with the help of area under this curve, okay. And this curve, this area will give you the work. So the shaded portion will give you the total work, which is nothing but minus 1 by 2 F1 plus F2 delta X. So this is how you can calculate the work of a force during a finite displacement for certain situations. Let us see about the concept of potential energy. So we know that the work of a weight we calculated just recently, that work is equal to Wy1 minus Wy2. So from the expression we can see that the work is independent of the path and depends only on the initial and final position, okay. So we can also we also know that from our previous knowledge that this work into height, it is also known as the potential energy of the body, okay. So we can see that the work is equal to simply the change in potential energy. So this one is the potential energy at first location, and this expression will give you the potential energy at the second location. So work through a finite displacement is also equal to the change in potential energy, okay. Similarly, the work of a spring, we know this expression, half kx1 square minus half kx2 square. Now this one is the potential energy of the spring at position 1, and this is the potential energy of the spring as position 2. So again we see that work of a spring through a finite displacement is equal to the change in potential energy of the body with respect to the elastic force, okay. So this E represents the elastic, okay, and G represents the force of gravity. Now when the differential work of a force is given by an exact differential, okay, then we can write this expression, work is equal to the change in potential energy, negative of the change in potential energy, or work from point 1 to point 2 is equal to simply the change in potential energy between point 1 and point 2. And one more important point, forces for which the work can be calculated from a change in potential energy are conservative forces. So this point is very important. Those forces for which we can calculate the work by simply calculating the change in potential energy are called conservative forces. For example, our gravitational force, this is the conservative force, and our spring force. Spring force is also a conservative force. So spring force is also a conservative force. Now let us see the relationship between potential energy and equilibrium. Okay. Now suppose when the potential energy of a system is known, then the principle of virtual work will be like this. So as we all know that for the application of principle of virtual work, change in work will be any work should be equal to 0, and we can also write it as minus delta V, because del U is minus delta V for the conservative forces, and we can write in this form also. So minus dV by d theta delta theta. So now for the potential energy and equilibrium, we have this expression, okay. Because it's delta U is equal to 0, so this thing should also be 0, okay. So dV by d theta should be 0, okay. So for the potential energy and equilibrium, we have change in potential energy with respect to theta should be 0. Now, so suppose for this structure, we have potential energy, total potential energy of this structure is elastic potential energy plus gravitational potential energy. And now we know this elastic potential energy is half kxb square. Okay, and this gravitational potential energy is wyc. And xb, you can get the expression for xb, and then you can simply put, then you will get half k 2l sine theta square plus wl cos theta. Okay, now for equilibrium, what we do, we differentiate this equation with respect to theta and put it equal to 0. So finally we will get this equation, L sine theta in bracket 4kl cos theta minus w is equal to 0. Okay, so we will get two answers, which shows that there are two positions of equilibrium for this body. Okay, so I think this is clear. So thanks for watching the video. Thank you very much. Have a nice day.